Hello everyone, my name is Chris Mason and I'll be talking today about the Btrfs file system. When we started the Btrfs file system, we really wanted to lay out a clear set of reasons why we were adding a new file system to Linux. This was especially important because the existing file systems are really generally very good. And so we wanted to make a general purpose file system that scaled very well to large storage. We knew that the development would take some time, and we wanted to make sure that it would be able to scale to the storage not just that we had today, but storage that was available in the future. So it was very important to us to focus on features that the existing file systems were missing. It's generally fairly easy to make the existing file systems faster, but adding new features within the constraints of their disk format can be significantly more difficult. So one of the things that we wanted to do was focus on the administrator. Make something that was very easy, very fault tolerant, something that was easy to configure and maintain over time, even as they were using the massive storage systems that we knew were coming out. Performance was important. We need to make sure that we're not dramatically slower than any of the existing file systems, but again, because the existing file systems are so good, we did not really want to go out and have a performance race with everyone. Generally, most of the file systems run at disk speed anyway. So while we wanted to perform well, we really wanted to make sure that it was the features that made Btrfs stand out from everything else. So getting onto those features, the first one is really a requirement today in the new file systems in Linux. It has to be extent based. And what this means is that instead of recording every single individual block that a file might use, we record a range of blocks. So instead of having one metadata entry for every 4K of the file, we'll record that a 1 meg range or a 256 meg range. Very large ranges of the storage are in use by a particular offset in a particular file. It makes the metadata itself much more efficient and allows us to record more information for each extent than we otherwise might have been able to do. We have copy on write, metadata and data. And what this means is that instead of directly overwriting any piece of metadata or any piece of data, we write any changes to a new location, and we change the things that point to that block or that extent. We change them to point to the new location. And this allows us to do many more advanced things, including the snapshotting and the checksumming that really make Btrfs stand out. So we have very space-efficient packing of small files, even though storage has become much larger. A lot of the files that we're putting onto it really haven't. And so there are a number of workloads where the workload itself is dominated by files that are quite small. And Btrfs is able to pack these together into the metadata B tree and save a great deal of space. We also have optional transparent compression. Right now we do that with zlib. But as a file is written or read, we have the ability to go ahead and compress or uncompress it and save quite a bit of space. And the way this works internally is that it's spread out across the CPUs on the system. And so even though compression does use a good amount of CPU time, we're still able to perform very well because we're able to make use of the large number of sockets that systems tend to have. One of the very important features is integrity checksumming both for data and metadata. This means that we're able to, when we read blocks from the disk, we're able to tell whether or not it's the correct data. And this is very important because very often, RAID systems are able to deal with hardware errors where a given sector read fails, but they might not be able to detect when the storage just returns the wrong thing. And with the integrity checksumming in Btrfs, we're able to detect incorrect data being returned from the storage, and if you're in a redundant configuration, we're able to ask another mirror if it might have a good copy of that data. Writable snapshots are one of the core features of the file system. It's really one of the things that the rest of the file system is built on. It was important that we be able to do snapshotting, not just read-only, but also have the snapshots writable and snapshotable again. In general, they're very efficient. We are able to have a large number of snapshots on the file system without degrading performance. And it's really one of the core things that the file system is built on. Online resize, defragmentation, device management, these were all added very early on in the file system as a way to show that the copy-on-write system that we have is able to add features that are difficult in other file systems. So we can online extend very, very quickly, make